Hello everyone, my name is Zhang. I'm a PhD student at the Chinese Academy of Science. Today I will introduce my paper according to this catalog. First, there are still some questions to answer before we are talking about graph embeddings. The first question is, what is graph embedding? In general, graph embeddings conveys a graph into a low-dimension space in which the graph information is preserved. Here is an example about a node embedding. You can see that the nodes in the graph are transformed into two-dimensional vectors, and the community struggle is also is preserved. The second question is, why use graph embedding techniques? Because it can represent the nodes in the network as low dimensional and they need vectors and can be convenient used as the input of the machine learning model. Graph embedding is a distributed representation scheme for nodes. The nodes in the network can be more intuitive and effective to return the relationship between the nodes in the original space. There are many researches on graph embeddings, and we briefly introduce three representative studies here. The first is graph factorization. This type of methods use metrics to store the relationships between the nodes and obtain the embedding representation of nodes by matrix decompositions. To obtain the embedding, the method factories the adjacency matrix of the graph, minimizing the following loss functions. Next, the second is deep work. It uses random walk to sample node paths in the graph to capture the co-occurrence information between the nodes, and then apply scheme model to learn the vector representation of nodes. This type of methods conveys graph to the node sequences with graph properties by random walk sampling, and then apply scheme or other model on the sampled sequences to get the representations. Third, SDNE. There are often non-linear relationships between the nodes in the real world, so the SDNE method believes that we should use deep learning models to capture the highly non-linear relationships between the nodes. It uses a deep autoencoder to preserve the first and the second order network proximities. Its input and output are the adjacency matrix and reconstructed adjacency matrix representatives. By optimizing the reconstruction loss, the global struggle information of the nodes can be preserved. The model used the first order loss function to make the embedding vectors corresponding to the adjacent nodes close, so as to return the local struggle information of the nodes. Then we will introduce our methods. We also adopt a struggle in SDNE, which can preserve the low-order graph struggle effectively. Our main model is also an autoencoder struggle. The encoder consists of multiple fully connected layer and performs non-linear mapping The input of the case lawyer is defined as xik, and output yk is calculated as following. We take the output of the encoder as the representation of the node I, and then restore it to the input of the encoder through the decoder. The calculation process of the decoder is symmetric to encoder. To preserve the second order proximity, the reconstruction loss is also defined as following. The model also needs to learn first order proximity, which means that if a pair of node I and node j are connected, they should be close to each other. To preserve the first order proximity, a graph-based loss function is defined as follows. Although the struggle preserving model can effectively learn low-order graph struggle information, it ignores the high-order graph struggle information, so we use a random walk to capture the community struggle information in the graph. To preserve the community proximity, the loss function is defined as a list function. And we need to sample several nodes as negative samples for learning the ground truth effective. So we define a noisy distribution to pick negative samples for node. The noisy the distribution we use here is actually a uniform distribution, and for each node, negative samples with different hopes should have different weights. So it is just like the nodes in the graph, if are far apart, and they should be thrown far away in the embedding space. So we use the shortest distance between nodes as the weight of the negative samples. The negative samples loss is defined as follows the functions. You can see here. The final objective function is this. You can see here. Is a weighted linear combination of the per objective loss. So we will introduce an effective multi-objective optimization algorithm MGDA-UB to optimize the final objective function according to the method. The resulting optimization program is defined as this. So we can see that we just communicate the gradient. The method will return the weight of each loss. So we will introduce our algorithm as follows. First, we use random walk to sample the node sequences. Then we selected the nodes from V as a mini batch B. Next, we use autoencoder to get the current representations. Then for each node V from B, we select the context nodes of node V from Works. Then we selected the neighbors of the node V. Then we will select the negative samples of node V. Then we can calculate the gradient about the representation Z and the weight of each loss. Then we will update the paragram theta with HGD. So if the paragram convenience, so we just return the final embedding representation Z. Then we will introduce our experiment. In order to evaluate the effectiveness of our methods, we use 4 public graph datasets. We will validate our method in 3 tasks. First is node classification task. Second is a graph reconstruction task. Then we will is node clustering task. In the node classification task, we will use MLP without activation for multi-label node classification and use LF3M for single label node classification. So you can see the results. Our method provides compactive results in multi-label and single label node classification task, and it shows that our method with MGDA is always superior to the other methods. This also demonstrates that the dynamic weights of multi-objective can help optimize the effect of the node classifications. Then is graph reconstruction task. In this experiment, we use inner products to measure the similarity of the vectors, and it shows that our method with MGDA performs not well. This is because it tries to reduce losses but does not effectively maintain the balance of the task. In general, it also shows that our methods can effectively learn low-order graph structural informations. Then is node clustering task. We use k-means algorithm to cluster nodes. The performance results shows that our method can effectively learn the high-order graph structural informations. Then, since we use distance-based negative sampling methods to improve learning representations, we investigate the contribution of the distance-based negative sampling to the performance. Some variants of our method are follows. Variant 1, our method learns the low or high-order graph information without the negative sampling. Variant 2, every negative sample has the same weight. Variant 3, it performs negative sampling based on the degree of the nodes. We saw variant 1, the results. The performance results shows that the distance-based negative sampling can in fact improve the ability to learn representation. The method without negative sampling does not perform well. Then the experiment results of the method with equal weight negative samples has improved, but there's still a gap between the distance-based negative sampling methods. Variant 3, if we do negative samplings based on the degree of nodes, it shows that does not perform well in node classification and node clustering. This is because negative sampling relies on too much on nodes with large degrees and neglects most nodes with small degrees. This results that demonstrate the contribution of the distance-based negative sampling methods. In this paper, we present a new graph embedding methods that focus on learning low and high-order graph structural informations. First, our methods fuse structural preserving model with random walk sampling, which can learn a multi-order graph structural information Second, the experiment results demonstrate that the distance-based negative samples can help improving the learning representations. In the future work, we will use GCN combined with consecutive learning to build a better model for graphs. Thank you. That's my PPT.